Good evening. I'm Dick Meserve, and I would like to welcome you to a Carnegie Capital Science lecture. Some of the most astounding scientific discoveries of the 20th century show that the universe is far stranger than it appears. Dark matter and dark energy, things we cannot see, are thought to make up over 95% of the universe. And dark matter and dark energy are at the center of some of the most profound scientific questions that we confront. What is the fundamental stuff of matter? What is the ultimate fate of the universe? And what is the nature of space and time? Although no one truly understands either dark matter or dark energy, we have good evidence that they exist. Some of the first and most convincing evidence for dark matter was actually discovered by Carnegie astronomers Vera Rubin and Kent Ford, working at our Department of Terrestrial Magnetism. And Vera Rubin is seated here in the second row. In their observation of spiral galaxies, Vera and Kent found that as stars increased in distance from the galaxy centers, their orbital speeds remained constant. The only explanation possible for this observation, given the laws of gravity, was that there had to be a tremendous amount of unseen matter in the galaxy's outer regions. As evidence has accumulated at Carnegie and elsewhere, the existence of dark matter has become an accepted fact. Another strange idea, dark energy, began to emerge about a decade ago. Carnegie astronomer Edwin Hubble had shown in 1929 that the universe was expanding. The law of gravity would indicate that the expansion of the universe should, over time, slow down. And with the availability of larger telescopes and more sensitive instruments, teams of astronomers in the 1990s set to the work of determining the rate of this deceleration. Carnegie astronomer Mark Phillips, now the associate director of Carnegie's Las Campanas Observatory in Chile, was a member of one of those teams before joining Carnegie. Much to the amazement of the team, the data showed, in fact, that the expansion of the universe is accelerating. The totally unanticipated force that is driving this expansion is derived from what astronomers term dark energy. Understanding it is perhaps one of the most puzzling and difficult questions now confronting science. We all know Einstein's equation, E equals mc squared, where E is energy, m is mass, and c is the velocity of light. This equation establishes the equivalence of mass and energy. Using this equivalence, astronomers look at the balance sheet and estimate that dark matter constitutes about 25% of the universe, dark energy constitutes perhaps 70%, and ordinary matter, the stuff around us, constitutes only about 5%. I mentioned at the outset that the discoveries of dark energy and dark matter represent some of the most astounding scientific discoveries of the 20th century. I make that claim because I find it simply astonishing that the vast preponderance of the universe is made of stuff that we cannot see and we did not even know existed until recently. Our lecturer tonight, cosmologist Rocky Kolb, will discuss the secrets of these strange concepts. He will explain how unlocking the secrets of dark matter and dark energy will illuminate even more profound issues, including the very nature of space and time and the connection of the quantum world with the cosmos. Dr. Kolb is currently the Arthur Hawley Compton Distinguished Service Professor of Astronomy and Astrophysics at the University of Chicago and chair of the university's Department of Astronomy and Astrophysics. He is also a member of the University of Chicago's Enrico Fermi Institute and its Kavli Institute for Cosmological Physics. His current area of research is the application of elementary particle physics to the understanding of the very early universe. And Rocky, I want you to know that we made a very special dispensation for you, that I know you come from Chicago, and we're even going to provide you with an ice storm so that you'll feel comfortable. A native of New Orleans, Dr. Kolb received his bachelor's degree from the University of New Orleans in 1973 and his PhD from the University of Texas at Austin in 1978. He was a postdoctoral fellow at Caltech and at the Los Alamos National Laboratory, where he was the J. Robert Oppenheimer Research Fellow. In 1983, Dr. Kolb founded the Theoretical Astrophysics Group at Fermi National Accelerator Laboratory. Then in 2004, he was the founding director of the Particle Astrophysics Center at the laboratory. He is a fellow of the American Academy of Arts and Sciences and of the American Physical Society. Among his awards is the 2003 Oersted Medal of the American Association of Physics Teachers and the 1993 Quantrell Prize for Teaching Excellence at the University of Chicago. In addition to authorship of over 200 scientific papers, he is a co-author of The Early Universe, the standard textbook on particle physics and cosmology, and the author of Blind Watchers of the Sky, a book about the history of astronomy for the general public. In 1996, he received the M Award of the American Aeronautical Society for this book. Maybe that's Emmy. Is that, no? It is often said that truth is stranger than fiction. As we contemplate a universe filled with dark matter and dark energy, we are confronted with the truth of this adage. Please join me in welcoming a college cosmologist who explores the dark side, Rocky Kolb.
Thank you, Dick. Thank you, Dick. And you really didn't have to arrange an ice storm for me. It has been pretty bad in Chicago. It was so cold in Chicago that the other day someone noticed a city alderman walking around with his hands in his own pockets. So as Dick said, I'm a cosmologist, and I'm proud of it. The job of a cosmologist is to not only understand what's in the universe, but to peer behind what we see and try to understand how it works. Now, in ancient times, it was thought that there were crystalline spheres, mechanical gears, and other sundry devices operating the universe, but now we try to understand the workings of the universe based upon the laws of nature. And I would, this evening, like to tell you some of the surprising results we have when we try to do this. So let me just jump right to the conclusion and tell you that we have a model of the universe that for the first time seems to be capable of describing everything that we see in the universe, all the phenomena we observe in the universe. Part of this cosmological model involves the current composition of the universe. So this is a question that's very simple that a fourth grader could ask: what is the universe made of? And the best idea that we have now for the composition of the universe is shown in this figure that we refer to as the cosmic pizza. Now, although the early universe was dominated by radiation, today the radiation in the universe contributes a very small fraction to the total mass energy of the universe, only about 0.005%. This figure also illustrates why chemistry is just not important. I don't know why chemists would dedicate their lives to studying the part of the universe that's only 0.025% of the total mass energy of the universe. I think they would be much better off studying elementary particles known as neutrinos, which in fact have a larger fraction today of the total mass energy of the universe, about 0.17%. It was discovered in the past 10 years that neutrinos have mass, and that discovery allows us to have an estimate of the total mass in neutrinos in the universe. Our astronomer colleagues look at stars and galaxies. That's about 0.8% of the total mass energy of the universe. Most of the normal matter, the neutrons and protons, are not in stars, but are in a hot gas in clusters of galaxies. And this hot gas is mostly hydrogen and helium. So we observe and can account for only 5% of the mass energy of the universe. 95% of it is dark. We don't know what it is. It's thought that 25% is in the form of dark matter, cold dark matter, and 70% is in the form of dark energy. Now, when I come to Washington, I often point out that in a true democracy, science funding would be distributed according to the representation in the total mass energy of the universe, but that doesn't work so well. So we have a model for the universe. Now, what does it mean when we have a model for the universe? I think that scientists have a different idea of what a model is than most people around. For instance, there was a famous economist who said that the construction of a model consists of snatching from the enormous and complex mass of facts called reality a few simple, easily managed key points, which, when put together in some cunning way, becomes, for certain purposes, a substitute for reality itself. Now, as a scientist, I don't want to find a model that's a substitute for reality. I want to find a model that is a description of reality. So to me, one of the challenges of 21st century science is to discover whether this cosmological model is a substitute for reality or a description of reality. Whether dark matter and dark energy will be the 21st century version of epicycles, or whether they are grounded in reality. So that's some of the issues I would like to discuss this evening. So let me back up by giving you a little bit of information about the framework for this cosmological model that leads us to the conclusion, the remarkable conclusion, that 95% of the mass energy of the universe is unaccounted for. The first scientific cosmological models only came about in the 20th century. It came about in the 20th century with a revolution in the way we view space and time. When we go about our everyday life, we have a view of space and time that's a Newtonian view of space and time. In Newton's great book, The Principia, he wrote about space and time. About space, he wrote that absolute space in its own nature, without relation to anything external, remains always similar and immovable. In the Newtonian picture of space and time, space is set, it's out there, it's absolute, and physics describes the motion of particles through space, forces acting over space, but space and time itself are fixed. This classical concept of space and time changed in the beginning of the 20th century with the work, of course, of Albert Einstein. In 1905, Einstein looked at equations he had scribbled while working at his desk in the Swiss Patent Office and came to the remarkable conclusion that the way people had viewed space and time as separate and distinct was wrong. That space and time were not separate, they were, in fact, relative. Einstein didn't stop there. 10 years later, he revolutionized the way people have viewed geometry, since the time of Euclid at least, with the realization that space and time can be curved and bent and warped. One of the first applications Einstein turned to apply his new theory of gravity was cosmology. Einstein expected to be able to describe a universe that was stationary, that was unchanging. So he tried to apply his equations to find solutions to his equations that described a universe that was unchanging in time, that was stationary. Now, I'm allowed to show one equation this evening and one graph. The one equation I'll show is the equation that describes Einstein's theory of gravity. Now, everyone's familiar with this equation, but actually it is 10 nonlinear partial differential equations in this equation. So since there are 10 equations, and we're going to use this to understand the origin of the universe, I sort of refer to them as the modern commandments of Genesis. Now, there are maybe some technical experts in the audience who will point out that there are 10 equations, but you only have to obey 6 of them. So it's just like the 10 commandments, right? It's widely believed that 6 out of 10 is a pretty good day for a lot of people. So Einstein looked at his equation, and the important technical point that I'd like you to appreciate is that this equation has something we call a left-hand side and something we call a right-hand side. And the left-hand side of the Einstein equation describes space and time, the curvature of space, the relationship between space and time, the expansion or contraction of space. That is on the left-hand side. On the right-hand side of the Einstein equation, so the description of the distribution of matter and radiation in the universe, fundamental particles, fundamental forces, all of the microphysics goes on the right-hand side of the equation. And Einstein's insight into gravity is that the distribution of matter and radiation tells space and time what to do, and it's the bending and warping of space and time that informs matter how to move in a gravitational field. So Einstein looked at this equation in 1917 after spending 10 years of his life developing it, and came to the remarkable conclusion that there are no solutions to his equation that describe a stationary universe. This disturbed Einstein. However, this now was the greatest discovery Einstein did not make. He should have looked at his equations and say, my equations tell me the universe is expanding. That's the way it's taught in graduate school for the past 50 years. However, Einstein looked at his equations and said, I can't find a stationary solution. There must be something wrong with these equations I spent 10 years developing. So he did something remarkable. He added another term to his equations that he described as a cosmological term. And the great advance in the last 80 years is to come up with a completely new name for this. Now we call it dark energy. So in 1917, Einstein developed the first scientific cosmology. It was based on 3 ideas. One is his theory of gravity, that there is a relationship between geometry and gravity. The second idea is that the universe is stationary. It does not expand or collapse. And the third idea is the existence of this cosmological term, or dark energy. Now, I said that this was the first scientific cosmology. The reason I say that it is now a scientific cosmology is that for the first time, a cosmological model can be disproven on the basis of observations and experiment. So in 1917, we had a cosmological model of one of the greatest scientists of all time, probably the greatest scientist of the 20th century, and this cosmological model of this great authority in science was overturned by observations of a basketball player. Now, this wasn't an average basketball player, but this was a basketball player who played on the last decent athletic team of the University of Chicago, the 1909 National Championship basketball team. We're still very proud of this. The starting forward on the 1909 National Championship basketball team, you all know, you see him there, it's Edwin Hubble, who after his stellar career in basketball at the University of Chicago went on to Carnegie observatories to discover the expansion of the universe. So Hubble discovered in 1929 that space expands, and Einstein's model crumbled. It's a science now. Observation and experiment can disprove theories, something that theorists do not like, but that's the way it goes. So it is the observation of the expansion of the universe that leads to the framework and the foundation of our modern theory of the universe, the Big Bang theory. Now, there are people who claim that something is just a theory. It's just a theory. I'm a theorist. When someone says it's just a theory, it's very annoying to me. And they say, well, it's just a theory and you should consider all possibilities. And I like to remind them that gravity is just a theory. And then when you approach the edge of a cliff, please consider all possibilities. But of course, now we know that the Big Bang Theory is much more than a theory. It is, in fact, a television program. So now it's completely accepted in American culture. So it's something that we can take as a given. So in the Big Bang Theory, the universe started with a bang 13.78 billion years ago last Tuesday. And I'll talk about events that happened in the first fraction of a second in the history of the universe when it was a hot primordial soup of all of the elementary particles. Now, we don't directly observe the universe in the hot primordial soup. The earliest picture of the universe we have is when the universe was 380,000 years old. So 380,000 years sounds pretty old, but it's a 13.78 billion-year-old universe. So this really is a baby picture of the universe. It's equivalent to a picture of a 50-year-old when they were 6 hours old. And eventually it evolved to be the rich universe we see today. And we'll talk about events that occurred there. One of the predictions of the Big Bang Theory is that there should be a background of radiation, and this, in fact, was discovered in 1965 by Penzias and Wilson, who discovered that the temperature of the universe today is 3 degrees above absolute zero, or minus 454 degrees Fahrenheit. And if you had eyes sensitive to microwave radiation, you would look up in the universe and see the microwave radiation, and you would see that the temperature of the universe is not exactly the same everywhere. And this traces back to events that occurred in the first second in the history of the universe. Now, as a cosmologist, I like to predict the past. I find it much easier to predict the past than to predict the future. However, some of my colleagues are brave enough to make predictions about the future and possible futures of the universe, and I thought I'd share some of these with you before talking about the present universe. So I'm going to show some possible futures of the universe on the cosmic timeline. So today, the universe is 13.78 billion years old, and we can look into the future and imagine that about in another 5 billion years, the sun will burn out. This causes some people great alarm, but in fact, there is a plan. We'll raise the terror threat to red. And in just 2 billion years after that, there'll be a response by FEMA. Since I'm from New Orleans, I just can't resist that. The universe will continue to expand and cool. It'll be, 100 billion years from now, hell will freeze over. Then, who knows? And maybe you can imagine billions and billions and billions of years in the future, the universe coming to an end. So much about the future. I like to study the past and the present. And now I'd like to talk about some surprising results when we study the present. We have a remarkable array of telescopes and satellites that allow us to take images of galaxies. I think galaxies are some of the most beautiful images of nature, but we take these images not just for their inherent beauty, but because we can learn something about the nature of galaxies when we study them. One question we can ask about a galaxy is, what is its mass? How much does it weigh? There are two ways of determining the mass of a galaxy. One is we can see how bright the galaxy is and estimate how many stars are there. We know the mass of stars, so we can estimate the mass of a galaxy by seeing how much light it puts out. We can also estimate the mass of a galaxy by measuring how rapidly it rotates. It is the mass that's producing a gravitational potential that's keeping the galaxy together as it rotates. And when we compare these two different methods of determining the mass of a galaxy, we discover something that we refer to as an accounting irregularity. The numbers just do not agree. They disagree by a huge amount. Now, one of the nice things about being a cosmologist is you don't have to be very good at arithmetic. To a cosmologist, 9 times 8 is 100. Pi is equal to 1. We don't worry about the few percent here and there, but this is too big of a problem to ignore. As Dr. Meserve mentioned in the introduction, this was a problem that traces back to work of Carnegie observers, Carnegie astronomers. Vera Rubin, in particular, at the Department of Extraterrestrialism. No, it's something else. In the 1970s, with her colleagues, measured this is the one graph, the rotational velocity of objects as a function of the distance from the center of the galaxy. And what she discovered is that the observed velocity is much larger than what would be expected if all of the mass was just contained in stars. What Vera and her colleagues discovered is that most of the mass of a galaxy is dark. Now, this is a remarkable discovery, and in fact, remarkable discoveries require remarkable evidence, so it's important that we have other pieces of evidence to tell us that most of the mass of the galaxy is dark. And this evidence, in fact, does come from studying galaxies and studying the phenomena known as gravitational lensing, or the bending of light by massive objects. Einstein predicted that space is curved around a massive object like the sun, and the path of light will be more complicated because space is warped around massive objects. And Einstein predicted that if we have an observer looking at a point-like source and there's a gravitational lens directly on the optical axis, you would not see a point-like source, but what you would see is the source spread out in something that's known as the Einstein ring. And it's the massive body that distorts space, that distorts the images of the objects behind it. And the more massive the lens, the more distorted the image would be. So by measuring the distortion of space, you can determine the mass of the lens. So this is an example of what a cluster of galaxies would do to a background image of galaxies. This is the cluster of galaxies, these orange things here. This is a computer simulation and an animation. It's not the real sky. But as you would move the cluster of galaxies across space, it distorts the images of what is behind it. And by determining how much the images are distorted, you can determine the mass of the cluster of galaxies. And this is done by observations from the Hubble Space Telescope and terrestrial telescopes now. It's seen in the sky. You can see the arcs, the Einstein rings of objects behind it. We can determine the mass of clusters of galaxies. And again, we're stuck with this accounting irregularity that there's much more mass than we can account for in the form of stars. So when you see a picture of a galaxy, there are missing pieces that we don't see. And we want to know, what are these missing pieces in a galaxy? Now, we don't see dark matter. No one has seen dark matter. However, in my office on the south side of Chicago, every month or so, someone comes in off the streets to my office, because I'm the chairman of the astronomy department, and comes in all excited saying that they can see dark matter. And I always ask them about the medication and why they got off of it. So we can't see dark matter, but we can ask a computer what a galaxy would look like if we could see dark matter. And the computer tells us that this would be an image of a galaxy if you could see dark matter. The galaxy we see would be in the center, the yellow disk, but it would be surrounded by a halo of dark matter where most of the mass of the galaxy resides. That is very dense in the center, and the density decreases as you go out, and there should be clumps of dark matter in the galaxy. This is what we don't see, but the dark matter is inferred by its gravitational effect. So we only see the tip of the iceberg when we look out in the universe. Most of the matter is dark. Some of this dark matter is this hot gas of hydrogen and helium, but most of it, it seems, is not normal matter. Most of the mass of the universe has to be in some unknown form of matter. And this is why it's a great time to be a theoretical physicist, because we can come up with ideas about what most of the mass of the universe is comprised of. How many times in the history of civilization can we actually ask this question and try to answer it? So there are various ideas. Some of the ideas have to do with maybe our law of gravity is wrong, that Einstein's theory of gravity or maybe Newton's theory of gravity is wrong. This seems to not be the case based upon observations of a cluster known as the bullet cluster of galaxies. Now let me spend a minute talking about this image. This is an image of two clusters of galaxies that have undergone a collision. There's a large cluster of galaxies here that's going in that direction, a large cluster of galaxies there that's going in that direction. These clusters of galaxies a few billion years ago underwent a collision. We can determine where most of the mass of these clusters reside, and they seem, this is most of the mass, the dark matter is illustrated in blue, resides in see the optical galaxies. Most of the mass in baryons, in normal matter, is not in the galaxies, but is in the hot gas that was shocked and left behind. So in the collision of the two clusters of galaxies, most of the baryons, which are in the gas, was shocked and left behind, but most of the mass passed right through like it was collisionless, and that's what we believe is the dark matter. So from this evidence, I don't believe that Einstein and Newton's gravity is wrong, that the dark matter must be something else. Now, there have been proposals for what the dark matter might be. People have proposed that it's planets. We used to talk about dwarf stars, but now if you're at a university, you have to be politically correct and refer to it as size challenge stars. The size challenge stars can come in various colors. Very size challenge stars are also light challenged. They don't emit very much light. Or it could be that most of the dark matter is in the form of black holes. These type of possibilities for dark matter is known by the generic name of MACHOs, Massive Astrophysical Compact Halo Object, MACHOs. But a few years ago, observations have told us that, in fact, the mass of the galaxy is not in the form of MACHOs, and most people think that the universe is not dominated by MACHOs, but the universe is dominated by WIMPs, weakly interacting massive particles. That presumably is a particle relic from the Big Bang. So let's ask, if this is a science and you believe that the dark matter is a particle relic of the Big Bang, how can you test this? And in fact, one of the ways you can test it is to try to recreate the conditions of the hot primordial soup in the laboratory. So if the dark matter is a weakly interacting massive particle that comes from the primordial soup, if you can make primordial soup in the laboratory, maybe you can make the WIMP. So if we could somehow collide things together at a high enough energy, we can recreate the conditions of the primordial soup to see if we can create WIMPs in the laboratory. And the tool that's used to do this are particle accelerators. This is an image of Fermi National Accelerator Laboratory outside of Chicago, and particles are collided together at very high energies in Chicago, out in the cornfields outside of Chicago, reproducing the conditions of the primordial soup to see if we can make WIMPs. Now, the idea of using an accelerator to learn something about astronomy sounds like a new idea, but actually it goes back to Galileo, who used a gravity-powered accelerator to learn something about the laws of physics, to learn something about astronomy. You all remember the story. Galileo went to the top of the Leaning Tower and he dropped 2 graduate students. And when he noticed that they hit the ground at the same time, he learned something about the law of gravity that was later used by Newton in his construction of the solar system. Now, we don't use a gravity-powered accelerator. We use one powered by Commonwealth Edison. But the product of particle accelerators like Fermilab is, in fact, the primordial soup. So that's what's made at Fermilab. We make the conditions that were present in the universe a nanosecond after the bang. We're recreating the primordial soup in the laboratory. And one of the things we can do in the primordial soup is look at the ingredients of the primordial soup. And there are photons, gravitons, bosons, electrons, croutons. There are all these particles in the primordial soup, but perhaps there is a secret ingredient that's the dark matter that we're looking for. We haven't discovered the dark matter yet, but perhaps one day in an accelerator, we will recreate in abundance what the universe is made of. So for the first time in 13 billion years, the WIMPs, the dark matter, will be made in abundance. This time not by the tremendous temperatures of the Big Bang, but through human imagination and ingenuity. We will recreate what's holding the universe together. And it's an exciting time now because it's also possible to detect relic WIMPs in sensitive experiments deep underground. The idea is you have some ultra-pure material, and if a WIMP goes through it at about 300 kilometers per second, it can nudge one of the nuclei in that ultra-pure material a little bit, and with sensitive enough detectors, you can detect its presence. The U.S. is presently mounting an experiment in a mine underground in a remote part of northern Minnesota. Well, that's redundant, right? Every part of northern Minnesota is remote. And right now we're looking for WIMPs. It could be that any day you will read about the discovery of a WIMP from this mine in northern Minnesota. And perhaps WIMPs are at the center of our galaxy right now, annihilating, producing gamma rays, positrons, neutrinos, or some other signal that we can look for with telescopes. So the race is on to discover dark matter. It might be discovered at accelerators like Fermilab or CERN. It might be discovered by satellites. It might be discovered by terrestrial observatories looking at gamma rays. This is an underground experiment. There are experiments underneath the ice of the South Pole which look for the signal of a WIMP annihilation in the center of our sun. It's an exciting time because many of us feel that we're on the verge in the next couple of years of discovering what the universe is made of, what most of the mass of the universe is. So the idea that we don't know what most of the mass of the identity of most of the mass of the universe is sort of embarrassing, but there's even more to the dark side than the dark matter. Let me turn back to the idea of dark energy. In 1917, Einstein proposed this cosmological constant, or dark energy, in order to have a stationary universe. In 1929, Hubble discovered the expansion of the universe, and the reason Einstein introduced the cosmological constant disappeared. At first, Einstein didn't believe the results of Hubble, but eventually the data became so compelling that even Einstein had to admit he was wrong. He said in 1934 that the introduction of the cosmological constant was his biggest blunder. He didn't realize that 64 years later, astronomers would find evidence for a cosmological constant. So the lesson is clear: you should never admit you're wrong. If Einstein had stuck to his original idea, he could have been famous. But instead, he said, no, I'm wrong. Now, the evidence for the dark energy comes from astronomers being able to trace back in time the expansion history of the universe. If dark matter dominates the universe will expand but will always slow in expansion because of the gravitational force opposing the expansion, trying to pull everything back together. But dark energy has the amazing property that it acts to push space apart, and it leads to space expanding eventually at an ever-increasing velocity. And in the past 10 years, astronomers have been able to look out in space back in time far enough to determine that this seems to be the track that we're on, that the universe today is accelerating, and this is the evidence for dark energy. Now, one way to think about dark energy is to imagine that it represents a fundamental property of space. Somehow, space has a structure that results in a density, an energy density, a mass density of completely empty space of 10 to the minus 30 grams per cubic centimeter. An incredibly small number. Now, how could empty space just by itself have an energy or have a mass? It represents the mass of nothing, empty space. So I'd like to mention some properties of empty space. So when I teach at the university, I like to ask my students to close your eyes and think about nothing. Some of them are really good. So let's imagine nothing. Let's imagine we have a region of space and we surround it by a hollow metal sphere, and we drill a little hole in it and hook it up to a vacuum pump and evacuate it so we can pull out of it all of the molecules and atoms and leaving behind a vacuum. We can also, at least in principle, imagine cooling this empty space, this region, to a temperature of absolute zero, freezing out all of the radiation. So what's left behind is nothing, the vacuum. Although we can remove the matter and radiation, what we can't remove is a fundamental property of nature of quantum uncertainty. The uncertainty principle of quantum mechanics implies that at any point in space, a particle and antiparticle can come out of the vacuum, exist for a brief instant of time, and then disappear back into the vacuum. So if you examine the vacuum on microscopic scales, it would not be a quiescent empty place, but would be a seething foam of particles and antiparticles coming out of the vacuum. So in some sense, nothing is something. There is another contribution to the energy of empty space that comes from theories of modern physics that's related to something known as the Higgs potential. Modern physics tells us that the quantum vacuum has a Higgs potential, and it is this Higgs potential that gives mass to quanta like quarks and electrons. And this Higgs potential has a tremendous energy of 246 billion electron volts everywhere in the quantum vacuum. Now, this Higgs potential is related to something known as the Higgs boson, one of the things that are motivating particle physicists to build huge accelerators looking for a particle known as the Higgs boson. We thought that we would be able to produce it at Fermilab, but I don't think we're going to be able to produce it at Fermilab. I think we're going to require the larger accelerator that's being built in Geneva. So I don't think we will make the Higgs boson at Fermilab, but I can announce, we have something even more exciting than the Higgs boson. We have the Higgs bison at Fermilab, much more massive than the Higgs boson. There is another contribution to the energy of nothing that comes from the possibility that there are extra dimensions of space. My friends who are string theorists tell me that there are well, I don't have any friends who are string theorists. But if I did, they would tell me that at every point in space there are extra dimensions that are wound up and we can't see them. This should contribute the energy to the vacuum. So there are all these ideas for the origin of the energy of the vacuum. However, we don't understand the unbearable lightness of nothing. The observed energy of the vacuum, if dark energy is described in this way, is 10 to the minus 30 grams per cubic centimeter. And all these ideas of virtual particles, extra dimensions, supersymmetry, Higgs vacua, give an enormous energy to the vacuum. So, for instance, virtual particles should contribute 10 to the 90 grams per cubic centimeter, a prediction that's off by 120 orders of magnitude. This is the worst prediction ever made in physics. And we don't really know how to do better. This is one of the reasons this cosmological constant is described actually as a cosmoillogical constant. We don't know the properties of dark energy. We don't know whether it's constant. And again, it's an exciting time to be a physicist, an astronomer, or a cosmologist because there are many projects like the Dark Energy Survey, LSST. Here at Carnegie, they're building the Giant Magellan Telescope, perhaps a satellite mission, the Joint Dark Energy Mission, which will measure in great detail the properties of dark energy to try to shed some light on our understanding or lack of understanding of the cosmoillogical constant. The American poet Walt Whitman said, "To me, every hour of the light and dark is a miracle. Every cubic inch of space is a miracle." I think people want to see miracles, but if you think of the cubic inch of space that's right under your nose, there's a miracle there. In every cubic inch of space, there's cosmic radiation, the remnant of the hot fireball of the Big Bang. There's dark matter, dark energy, virtual particles, a Higgs potential, perhaps extra dimensions. Every cubic inch of space is a miracle. Now, the fundamental problems are the identity of dark matter and dark energy, and to really understand dark matter and dark energy, we are going to have to connect the inner space of the quantum with the outer space of the cosmos. We've seen that we can't understand the largest things in the universe without understanding the smallest. We look out at universities, and we see a department of astronomy, a department of physics, a department of zoology, biology, but nature itself is not so easily divisible. To understand one thing in nature, you have to understand everything in nature. John Muir said, when we try to pick out anything by itself, we find it bound fast by 1,000 invisible cords that cannot be broken to everything else in the universe. To understand the largest things in the universe, we're going to have to understand the quantum nature of the world, the micro-world. To understand outer space, we have to understand inner space. So the takeaway message this evening is that there is a dark side of the universe. We see a few bright lights when we look out, but 95% of the universe is dark and mysterious. I started out talking about the birth of modern cosmology with Albert Einstein's work, and sometimes I wonder how Einstein would have reacted to this mystery of dark matter and dark energy, and I think he would have enjoyed it. Einstein said the most beautiful thing we can experience is the mysterious. To him, it was the source of all true art and science. Cosmologists today are no stranger to mystery. 95% of the universe is a mystery. Although it's a mystery to us now, in the nature of dark matter and dark energy are our cosmic questions, our generation's cosmic questions, I know that someplace out there in the world there is a child with the genius, imagination, and courage to reach out, reach up, and connect the inner space of the quantum and the outer space of the cosmos, to answer our cosmological questions, and more importantly, to develop cosmological questions of their very own. Thank you.
Well, thank you, Rocky, for a really remarkable lecture. You covered an enormous amount of terrain in a fascinating way. We do have an opportunity for a few questions. There are microphones in each of the aisles, and let me suggest that anyone who would like to ask a question, there's an opportunity here to just come up to the microphone, and we'll call on you one at a time. And we do have a limited amount of time this evening, so I apologize for that.
We also have a limited amount of answers.
Please.
Okay, I've kind of asked this before, nobody answers it. In other words, what is space expanding into? And in addition to that, if there is dark matter, why isn't it part of the regular matter too? In other words, is it like oil and water where they don't mix? Or is there dark matter right in front of us?
Okay, so the first question is, what is space expanding into? And I think the way to visualize the expansion of the universe is not an explosion of galaxies out into empty space. Rather, it's an explosion of space. It's space itself that is expanding. So there is no center to this explosion and no edge that the galaxies are expanding into. So it's an expansion of space, not an explosion of galaxies into space. Now, I've given you an answer, and I appreciate that this is a difficult concept, and I spend weeks in teaching graduate students at Chicago trying to get them to appreciate this. But the way to view it is it's an explosion of space, not an explosion of galaxies into space. So the universe is not expanding into anything. It's like space is being created between all of the galaxies. So if you imagine an infinite loaf of raisin bread where the galaxies are raisins, as it's heated, the yeast works and it expands. But it's difficult to wrap your mind around the idea of an infinite loaf of raisin bread. Now, the other question was, is dark matter around us? And dark matter presumably is all around us, but it is segregated from normal matter. So if you imagine the formation of a galaxy, starting with normal matter, neutrons, protons, pizza toppings, whatever, and dark matter together, as it collapses, the normal matter can dissipate its energy and fall deep into a potential well. So the normal matter becomes very tightly bound. The dark matter, if it does not interact with anything, is not able to lose its energy and fall into the potential well, and would surround the normal matter in a halo. So I showed a picture of normal matter concentrated, embedded in a halo of dark matter, and we think that that is what a galaxy looks like.
So it's right here now?
It's right here now.
Okay.
Let's go to the other microphone, please.
Are you familiar with the theories of Moshe Carmeli,
No.
relativistic cosmology, in which he claims by modifying the equations of relativity it isn't necessary to have dark energy and dark matter?
There have been many proposals, and some of them very interesting and exciting, to modify general relativity, modify gravity, even modify Newton's laws to explain the observations without the existence of dark matter. And that may turn out to be the answer. But I think observations like observations of the bullet cluster suggest to me that that's not the approach that's going to work. So we don't know the answer, and it's premature to say what doesn't work. But to me, the idea of modifying gravity is not going to explain dark matter. I think the most promising possibility is that it is in this new type of elementary particle that will be discovered any day.
Please.
Thanks for a great talk. I came across a quote I wanted to ask you about in a book that was published in 2000. You were quoted as saying...
Who was quoted?
You.
I was misquoted.
Well, this is why I wanted to ask you.
Next question.
You're quoted as saying that you found any cosmological model with a cosmological constant term as being unspeakably ugly. And I was wondering if that's accurate, and if so, what you meant by it.
Yes, it is accurate. I did say that the cosmological constant is unspeakably ugly. And actually, I think that the dark energy in the cosmological constant will be the ether of the 21st century. That I think it's going to end up not being there. The answer to explain the observations will be something that's so much more complicated and beautiful than we envision now, that it will point the way to new revolutions in physics.
Thanks.
Please.
But don't quote me on that.
That sort of follows into my question. You had started out by saying that what Einstein had introduced, which turned out to be this explanation for dark energy, once we discovered that the universe was expanding, it turned out, okay, this is false. But does that mean then that the concept of dark energy is not grounded? You see what I'm saying?
Well, in Einstein's universe, there was a curvature of space that wanted to pull things together, and his cosmological constant that wanted to push things apart. And he imagined that they exactly balance, but they don't.
Okay.
So the cosmological constant of dark energy still would want to push space apart, but it's not this finely tuned, exactly balanced universe. So perhaps Einstein introduced the right thing for the wrong reason.
Got it. Okay. Thank you.
Please.
Since you've come all the way from Chicago to Washington, I'll ask you a purely Washingtonian question. In light of the budget cuts to both the Fermi Labs for the International Linear Collider and both the NOVA project in Minnesota, how's that going to impact the ongoing research where we go from theory to fact?
Boy, that's a very good question, and I have written my congressmen and my representatives and told them that this is a very bad thing to do because we're right on the verge of great discoveries, and we're going to end up having the French discover what dark matter is. So
we don't want that. Thank you.
So I think it was not a good thing to do.
Thank you for your lecture. My question relates to, you had mentioned in your talk about the expansion of the universe speeding up. I had two questions related to that. Where is that energy coming from? And then how would that impact the principle of conservation of energy within a closed system?
So that's a good question. And I spend a lecture or so when I teach talking about that. So let me give you the 30-second answer that it's like energy is being created, but it's because of conservation of energy. So what you have to take into account in the energy balance equation is gravity. So once gravity enters, it's not as simple as saying the total energy is the same, because you have to take into account the energy in the gravitational field. And it's the energy in the gravitational field, which is negative, is balancing the books. So you could still have something that ends up looking like conservation of energy, even though it looks like energy is increasing.
Okay,
that made sense to me.
Two more questions.
Yes, I have a somewhat naive and paranoid question. If we were actually to recreate the conditions for the Big Bang, as you suggested at one point in your lecture, what is to guarantee we won't have another Big Bang with somewhat, shall we say, undesirable consequences?
Well, one of the questions, another way of answering that question is, can you go into your basement and make a Big Bang? And one of the things that seems to be required is a space-time singularity. And you just can't go to CVS and buy a space-time singularity. And even if you had a space-time singularity, and you would create essentially a universe in your basement, the way the geometry works is it would be hidden by a horizon and you'd never be able to see it.
So it wouldn't be unpleasant at all?
No, it wouldn't be unpleasant. You wouldn't know you've done it, though.
Okay, the last question at this microphone.
In the contribution to the vacuum that you said was about 10 to the negative 30th grams per cubic centimeter, you described a list of things that could contribute to that, but all of those were, plus or minus this, and plus and minus that, and plus and minus this. All of that averages out to zero. Why would there be a residual, positive amount, even as small as it is? Wouldn't in the long run it would still all average out to zero? How would it have any effect, and what does that affect for us today?
We don't have a clue. That's a great question. I wish I knew the answer to that question. So you have enormous positive numbers and enormous negative numbers that cancel to 119 significant figures. Does that make sense to you? Do you believe that?
Well, how do we know that it's, how do we, what is it doing for, how do we know that there's 10 to the negative 30th gram? What is that doing?
So if there's a cosmological constant or dark energy that is responsible for the observed acceleration of the universe, then we can determine that the energy density of empty space is 10 to the minus 30 grams per cubic centimeter. So the astronomers are telling us it's 10 to the minus 30. The physicists are telling us, no, it's 10 to the plus 120. Something's wrong. And it's this great tension that between observations and theory that makes it so exciting to work on.
Do you have your own speculation as to the resolution of this incredible tension?
Yeah, I have my own speculation.
You want to share it? Or?
Well, I think that it's just conservative answer that the way we've been doing cosmology since 1922 is not quite right. But none of my colleagues want to hear me.
Well, we've had a lecture that has revealed to us, I think, very clearly that we live in a very, very strange place. But we've
Washington?
And Rocky has provided us with a very fascinating tour of it. Please join me in thanking him for a fascinating lecture.